Hello, we are from Group 12. We'll be presenting Fluid Catalytic Cracking. So before we start, we would like to introduce our team members and their respective presentation. The first one is Shamini Rajendran, will be presenting catalyst screening. The second one is Nur Musfira Mustafa, will be presenting reaction mechanism. The third one is me, Mubarak bin Muhammad Taufik, will be presenting introduction and also determination of basis for reactor design. And finally, Shaima Tariq will be presenting reactor selection and reactor design. So firstly, what is fluid catalytic cracking or FCC? FCC is a chemical reactor to convert oils with high boiling points into fuels with lower boiling points with presence of catalyst. So the FCC is divided into four main parts. The first one is the preheat system, which functions to reduce crude residue. The second one is the riser, where all the reactions are carried out in this process in endothermic behavior. The third one is the reactor, which aims to separate the catalyst deactivated of the cracked vapors and passing the catalyst used downward through a stream stripper part to the regenerator. And finally, the regenerator part is for the regeneration process, which we will discuss more later. So the diagram shown is a typical high conversion refinery for fluid catalytic cracking process. As we can see that the fluid catalytic process that we are on is only at the alkyl unit, where only LPG and gasoline are produced. The fluid catalytic cracking process breaks large hydrocarbons by their conversion to carbocations, which undergo a lot of rearrangements. The figure shown is a simplified schematic diagram that exemplifies how the process breaks high boiling point straight chain alkene, which is also called paraffins, into smaller straight chain alkenes, as well as branch chain alkenes, olefins, and also cycloalkenes. Some of the smaller alkenes are then broken and converted into even smaller alkenes and branch alkenes, such as the gases ethylene, propylene, butylene, and also isobutylenes. The olefinic gases are valuable for use as petrochemical feedstocks.
I'm Shamni and I'll be presenting about the catalyst screening. So the design and operation of an FCC unit is largely dependent upon the chemical and physical properties of catalysts. So the desirable properties of an FCC catalyst are good stability to high temperature and steam, high activity, large pore size, and also low choke production. The FCC catalyst has four major components: crystalline zeolite, matrix, binder, and also zip filler. So the zeolite is the primary active component, while the matrix component of an FCC catalyst contains of alumina, which also provides catalytic activity side and in a larger pores that allows entry for large molecules than the zeolite does. The binder and the filler components provide the physical strength and integrity of the catalyst. The binder is usually a silica solution, and also the filler is a clay kaolin. Next is the properties of zeolite. So zeolite has a high surface area and it's a uniform micropore size, high hydrothermal stability, intrinsic acidity, and also its ability to accommodate active metal species. The zeolite used in FCC are type X, type Y, and also ZSM5. So the X and Y zeolite are referred to as phagosite FAU, and ZSM5 is referred to as mobile 5, which is MFI. So FAU is the standard fluid catalytic cracking catalyst, and MFI is to boost the propane, it's additive. To compare the stability of X and Y zeolite, so the X zeolite has a lower silica alumina ratio than the Y zeolite, and therefore it makes it less stable. Besides that, it also has a lower thermal and hydrothermal stability compared to Y zeolite. While for the ZSM5 is a versatile zeolite that increases the olefin yield. However, the ZSM5 has a very small pore compared to Y zeolite, therefore it has a greater tendency to get clot and choking, and has a high diffusional resistance. As you can see from the table on the right, the production of gasoline is higher for Y zeolite compared to ZSM5, and the choking percentage is lower for Y zeolite, which is only 1.46 compared to ZSM5. So the choking percentage for ZSM5 is higher compared to Y zeolite. Therefore, the main zeolite type used in FCC is FAU. So, the success of ultra-stable Y zeolite in fluid catalytic cracking is partly due to the accessibility of FAU for large molecules. The term ultra-stable Y zeolite refers to FAU where the silica to alumina ratio that is greater, which is 6:1. And this is usually achieved through dealumination by steaming, and by decreasing the alumina content the acid site density is reduced, and when the acid site density is reduced the hydrogen transfer reaction is suppressed, which leads to an increase of the alkene content of the product and decreases the formation of aromatics and alkylanes. Based on the comparisons, we can conclude that the Y-zeolite is the most suitable catalyst to be used in FCC.
Now I will continue the presentation on reaction mechanism. The important part in reaction mechanism is the development of kinetic rate equation. Chemical equation is A forming into B plus C plus D, where A is gas oil, B is gasoline, C is coke, and D is light gases. There is some basis applied in selecting the mechanism, where the first basis are surface reaction as the rate determining step by using Langmuir, Hens-Wood, Hogg-Watson kinetics. Second, assume single-site surface reaction. And third is fresh catalyst, where no coke formation. Now we can start developing our kinetic rate equation. First, we have to identify the equation for adsorption, surface reaction, and also desorption. Next, we have to develop the net rate of adsorption of the species, which is equals to rate of attachment minus the rate of detachment. In adsorption and surface reaction, capital K stands for equilibrium constant for the specific species. Since concentration of A at active site and concentration of B at active site cannot be measurable, we have to replace it with variables that can be measured, such as partial pressure of A and partial pressure of B. Now we include some assumption where adsorption and desorption process happen fast, where Ka and Kd are very large compared to Ks. Thus, RAD over Ka equals to 0 and Rd over Kd equals to 0. Now we apply this assumption into equation 1 and equation 3 to form new net rate equation, which is equation 4 and 5. The new net rate equation are substituted into surface reaction equation, which is equation 2, and being simplified to form equation 6. Now the overall partial pressure equilibrium constant are applied into equation 6 to form equation 8. Since we cannot measure concentration of active site, we will eliminate it from equation 8 by site balance equation, which is equation 9. The equations are further simplified in terms of CS, which is concentration of active site. Equation 10 are substituted into equation 8. Let K equals to Kc, Ks, Ct. Thus the desired rate expression are developed as stated in slide. The next part is the performance catalyst testing. For our process, we chose MAT test, which is a microactivity test. In this test, a small sample of catalyst is tested in fixed bed. The test contacts the catalyst and feed for prolonged periods, during which the activation of the FCC catalyst proceeds and coke and temperature profiles may develop over the catalyst bed. We also include the MAT experiment data for FCC catalytic performance.
Moving on to the determination of basis for reactor design. As a general statement of the basis objectives in designing a reactor, the aim is to produce a specified product at a given rate of reaction from known reactants. In this case, we are using the reactant of gas oil. In this paper, we will be using the reactor of fluidized bed reactor. The reason we are using this is to obtain the basis of the optimal operating conditions for industrial FCC process. So as we can see from the slides, the operation conditions includes the reaction temperature of 820.0012 Kelvin, weight hourly space velocity of 2, catalyst to oil ratio of value 10, octane number of 97, and also a conversion of 87.6075%. The fluidized bed reactor is divided into two main parts of the regenerator and also reactor. The object of the regenerator is to remove the coke that builds up on the catalyst in the reactor without damaging the catalyst. Many studies have been made on the burning rates of coke in a fluidized bed of cracking catalyst. So by analyzing the regeneration model, we have obtained the optimal operating conditions, which has the variables of coke in generated catalyst has the values of 0.000362 weight percentage, which is very low. And the second one is that we have the flow rate of F8 of 0.55 kilomole per second, and also regenerator temperature of 968.58 Kelvin. Before we have all of these values, we have the assumptions of: firstly, the mass transfer resistance from gas phase to solid phase can be ignored. The specific heat capacity of gas and compound are constant. And finally, the cyclones at the generator return all the entrained catalysts. A few observations have been made from at higher temperatures of more than 1300 Fahrenheit or more than 700 degrees Celsius. The burning rate is very high. Oxygen availability limits the burning rate through the small size of the fluid cracking catalyst, eliminates or minimizes diffusion as a reaction barrier at normal regenerator temperatures. Over the years, the regenerator temperatures have increased due to better metallurgy and the need to burn all of the carbon of the catalyst to restore the zeolite catalyst activity and product selectivity. The catalyst used in this FCC process is dy zeolite. In here, we have obtained the parameter and also the values. As we can see, the significant one are the volume of catalyst of 65 cm3, the reactor pressure of 2.28 atm, the diameter of catalyst particle of 0.0075 cm, the total pore volume of 0.37 cm3 per gm, and also regenerator pressure of 2.588 atm. These are all mostly the values obtained from the Handbook of Petroleum Processing.
For reactor selection, we choose fluidized bed reactor for FCC. This reactor consists of a riser and a regenerator. The regeneration process is done by feeding high velocity air into the regenerator to oxidize the coke on the surface of the catalyst. Catalyst will be reactivated and the coke will produce carbon monoxide and carbon dioxide. The main advantage of this reactor is the efficiency of heat exchange. Hot regenerated catalyst will aid the vaporization of feed gas oil, while the heat produced during regeneration of catalyst will be supplied to the endothermic cracking process in the riser. Assumptions made in designing the reactor are plug flow model, first order reaction and decay, ideal gas behavior, no pressure drop and volume change, and finally steady state behavior. In our study, FCC is represented by a 4-law model as shown in the left diagram. However, for simplification purposes, we have simplified the complex reaction into 3 parallel reactions as illustrated in the right side diagram. Here, you can see the essential equation used in designing the reactor, from stoichiometry equation, rate of reaction, decay law, and also the design equation. We start our calculation by setting the amount of gasoline to be produced by the reactor. From there, we will be able to calculate the inlet flow rate and concentration of gas oil. By combining the stoichiometric and rate of production of each product, we can calculate the overall rate of consumption of gas oil. We have derived the catalyst activity equation as shown in the slide. By integrating design equation number 7, we have calculated the weight of catalyst. We found that the catalyst weight needed is 4,826.62 kg, while the volume is 5,362.91 dm cubic. From literature review, the ratio of height to diameter of reactor is approximately 30:1. So, we found that the reactor height is 183.17 dm and the diameter will be 6.11 dm. Finally, we compared the reactor sizing for reaction with decay and without decay. From our finding, the reactor sizing without decay is only about 1% smaller than with decay, so the change in sizing is not very significant. This concludes our presentation on fluid catalytic cracking. That's all from us. Thank you.